record, and let's get going. So the exam's done. I'll be grading part A throughout the weekend. So far, results look pretty good. I don't see major issues. I do have some time probably next week during the lab, and I'm in a different location right now. I'm at my sister's house doing the class, and I got a window behind me which sometimes takes the brightness out. You won't be watching me much, but anyway, I will have some time to answer questions about any of the problems on the exam that you are unsure of and you want me to go over. Office hours is always available for that as well. We're going to talk. You do have a homework assignment due tonight. I pushed it to after the exam. If you need more time, please let me know before the due date. That's always a good practice. I understand that there may be other midterm exams going on this week. A lot of people divide their semesters up into about thirds when they schedule exams, and I perfectly understand that. Just let me know what you got going on. I'm going to do a worksheet problem for you. We're going to do some polling, okay, as we normally do. I don't have many questions on the worksheet. I do also want to show you about resources to use in the rest of this class, because now we're in the home stretch, only about 3.5 weeks left. So we're in the home stretch of this class, and then any other classes that are calculational that you might be taking during the rest of your time here at Washington College. And so that's kind of my plan. And I hope to demonstrate the value of some of these. And show of hands, did anybody invest a lot of money in a very, very expensive calculator? I'm thinking something like the TI Inspire, which is well over $200. Some of the TI 80 series are pretty expensive too. Does anybody own one of those? Anybody want to raise your hand and say, yep, I plunged $200 for my education to buy an expensive calculator? Yeah, and the answer is you don't have to. Okay, good. I had one, but it was given to me because of where I was working, and I have an older version of the TI, and they're pretty pricey. But there are resources on the web that will cause the person who spent a little extra money on a great calculator, it equalizes the playing field for you. Okay, and I want to show you that, and I think they're good. As a science teacher, we're not worried about how you do the math. We're worried that you can get the math done, if that makes sense. Okay. And I do notice that often for some of you, it's not really the physics. Sometimes it's the physics. You don't have the physics concepts down that cause you to miss problems, not get things right. But sometimes it's simply the math. Okay. You just can't get the math right. And so hopefully I'll give you some hints on that today. All right. So I'm going to start sharing my screen with you, do our obligatory couple of, where is it? There it is. A couple of polling questions. And yep, you are seeing my screen there. Hopefully you recognize that apparatus. It's in any science novelty shop. You can buy, they're called Newton's balls, right? You pull one back on one side and you let it go, and none of the middle ones move, but the one at the other end, 5, starts moving. And one of the two topics we're talking about today, we're revisiting collisions. And that's an oddity of the order of topics that our textbook does, way it orders the chapters. We got to go back and talk about collisions again now that we know a little bit about energy. So let's start this, and got to go all the way to the bottom. There it is right there. And what's the answer? And hopefully you realize this. Yeah. Yeah, fairly straightforward, and most of you are jumping on the exact answer. All right, 20 of 25 in, and the overwhelming majority got it. You understand what it means. So we'll end it, and I'll share the results with you. And the answer is, of course, A and B. When we talked about collisions in chapter 9, all we were doing was conserving momentum. And let me grab a pen here to draw. Come on, get out of the way. And that meant that, what's the equation that you solve this with? The initial momentum, that's an I right there, has to be equal to the final momentum, right? That's conservation of momentum. And then, of course, somewhere, you have to either know it or look it up. Momentum is equal to the mass of an object times the velocity. And in this case, there's 5 potential things that could move, right? All the balls. But the problem starts off, the initial momentum is one of the masses times the velocity of one initially, plus zero, because everything else is zero, is equal to the mass times the final velocity of 5 is what this problem tells you happens. And in this case, these balls, doesn't specifically say it, but they are all the same mass. Every one of them has mass little m. Every one of them might be 3 grams or something like that, hanging from some strings. And you hopefully have seen this. So that's the equation. Well, the masses cancel. And in this particular case, we find that velocity 1 is just transferred to velocity 5 at the end. But that begs the question, I guess, why is it that 2, 3, and 4, why didn't they move when 1 smacked into them? And the answer was the second condition that you all jumped on, the energy. And, I could write E if I wanted to here, but there's no change in potential energy that's appreciable, right? It is only initial kinetic energy is equal to final kinetic energy. Okay, so you got to know what kinetic energy is, right? You have to either look it up or you have to know it. 1/2 the mass times the velocity squared. Well, if you put that condition on the momentum equation, there is only one mathematical possibility that results out of that, and that is that for objects that have the same mass, all the velocity of one goes to the velocity of the fifth one. And I showed that for just 2 masses in the pre-lecture video for today, where if 2 masses collide, one initially at rest, the one that's moving at the start stops and its velocity goes right on to the velocity of the other object. They just exchange velocities. The one that was at rest starts moving at the same speed that the thing hit it at, that the one that came in and hit it at is. And that's a requirement that comes out of that. Now, I'm going to do a problem. So this becomes, of course, a series of 1/2 mass times velocity 1 squared plus 1/2 mass velocity 2 squared. You add them all up. In this case, there's only one thing moving at the start. So all of this stuff would just be 0, has to be equal to 1/2 mass 1 velocity 1 final squared. And I guess this is initial right here, isn't it? And you just keep adding them up. And we'll go on more on that when I actually do a numeric problem. But people ask me, well, how do I start these problems? And the construct is what we're talking about here. You look at what the initial state is. What's the initial momentum? What is the initial kinetic energy? And then you go, okay, now after the event occurred, in this case, a collision. In the case of other energy type problems, it's okay, the ball slid down the hill. The person ran up the stairs. What's the final state after that event is done? What's the final energy? And we also have to, in energy problems, include potential energy and any work done. Are we working against any springs? Are they being compressed? And you look at the final momentum in a collision case like this. Now, just a couple pieces of vocabulary. When both momentum and energy are conserved, we refer to it as an elastic collision. I don't know why they picked that name, but that's the term of art, okay, for energy and momentum is conserved. If only momentum is conserved, we call it inelastic, not elastic. I didn't invent those words. You'll never get a problem in an exam situation from me, right or wrong, based on knowledge of those words. I will tell you, you have an elastic collision in which both momentum and energy are conserved. Now set up the problem and figure out the velocities, okay? If there's only momentum conserved, I will say something like there's an inelastic collision conserving that does not conserve energy, find the final velocity, something like that. Under inelastic collisions, the ones where only momentum is conserved, there is a special case that we did when we did collision problems back in chapter 9. If the 2 objects stick together after the collision, like they got Velcro or maybe they're clay and they mold together, cars stick together after collisions often, and sometimes in sports, tackling causes the 2 colliding bodies to stick together. Okay, we call those perfectly inelastic. And that's a term of art that means that after the collision, the 2 objects are stuck together as one. Okay, nomenclature. Again, I'll always have that in the problem statement. I might use the word, but I'll self-define it in the problem for you. Okay, so the question might be, where does the energy go in an inelastic collision as compared to an elastic collision where it's conserved? The kinetic energy just shifts from the initial state to the final state. And hopefully you realize that in many inelastic collisions, there's deformation. Like when two cars collide, fenders and bumpers get bent all out of shape, right? They give off heat and energy is, and they give off a lot of noise and sometimes even light. They spark and all that sort of thing. That's where the energy goes, and that's why in inelastic collisions we aren't able to conserve energy. Elastic collisions are often, you can tell that they're elastic because of the sound they make. Okay, Newton's balls, when they come together, very distinct, quick click, and then the collision's done. Billiard balls are the same way. Okay, very distinct click. It doesn't, you don't get the impression that there's a thud where all kinds of energy is dissipated to deforming objects and causing heat to be generated. Not the case for inelastic collisions. All right, any questions on the difference? I'm going to do a problem today. The next time you'll see a problem on this is going to be the homework from chapter 10. And then after that, probably the next time there could be a problem on inelastic or elastic collisions would be the final exam. All right. Which, by the way, my understanding is it is on the Monday of exam week. And it's the morning, I forget what time the morning exam starts with. It's either 9 or 9:30 on the first day. And so my current plan is I'll be releasing the exam the day before Sunday, and it will be due uploaded and done in Mastering Physics, just like the midterm here was before the end of the exam period, which is on Monday of the first day of the exam week. All right, questions? All right, I'm going to move on to the next one then, spend a lot of time on that, and I will do a problem on it. It's important. The other thing we had to talk about in the lesson last night for today is power. And stop sharing that. Go on to the next one. Just some definitions of power here, some vocabulary about power. And so which of those is false? All right. Yeah, it's been a busy week for everybody, hasn't it? Most people are getting this right, but there's still a lot of things that I'm kind of questioning, wondering why they think that. And I got 20 people in. I had 21 before. Somebody started and just tuned me out, not playing this morning. I'm going to end and share the results with you. And of course, the answer is all of the above. And so pretty much this is the laundry list of what you need to know about power. Okay, it is a scalar. You know, that's the great thing about work and energy problems. Work has one aspect of it that requires you to do vector manipulations, things like finding a component, because we said work was equal to the force parallel, that's the symbol for parallel that mathematicians use, times some displacement, right? And so the one piece of vector manipulation you might have to do is to find a parallel component of a force. Once you are done with that, vectors are completely out of the problem when you're working with work, energy, and power. Scalars, add them. They add like numbers. And so that's good news. That's why a lot of people like energy problems. Once you understand the concept, the mathematics is simply bookkeeping, much like an accountant would do. You've got various energy accounts, you get to move around, but they add like scalars. You never have to worry about finding components when you're working work and energy problems. Power is the rate at which work is done. Okay, we define power as, and that's a capital P, just to confuse you with momentum. I didn't do it. This is a capital P as opposed to momentum, which is typically a lowercase p, which you certainly can't tell from what I just wrote right there. And it is the work done over the time interval, right? Okay, so we just take that, put it right in there. That's what it is. And if you can figure out the work done via figuring out change in potential energy, change in kinetic energy, something like that, perfectly acceptable way to get the numerator, the work done, but that's how we define power. If I do put that in, then I guess I would have the force parallel times delta x over delta t, which is just the velocity. So it is also the product of a parallel force and a velocity. So C is true. And then if you look at the units of work and energy, it's joules. The units of time is seconds. So power does have units of joules per second. It's conventional to rewrite joules per second as a watt. Okay. And that makes all the above statements true. So the 90 of you that went that way, just about half the people that answered it. I guess the people who went A through B, you're not wrong, but you should recognize that all the other things that we have up here are also true. All right, last one, and then I'm going to do a problem and show you what I think is a great resource. Stop sharing this and move on to the next one. You might need a calculator for this one. Early on a Friday, if you can't do this in your head, I get it. But look at a couple things. The time intervals here are the same. Oops, that one's not. That one and that one are the same. This one is significantly longer. These heights are all 10 meter for A through C, but that height is twice as big. And the hint, of course, is that gravitational potential energy is mgh. So I guess power here would be equal to the work done, which is the change in gravitational potential energy. That's U sub G. That's lousy looking. Over the time interval. And this is one of those times where my advice, G, don't try to make it 9.8. Make it 10 meters per second squared. It'll get you close enough. It'll get you to the right answer. All right, we got 19, almost done here. Pull that calculator out. I'll let you go for 2 minutes. Got to stop. All right, I'm at 20. We're going to stop it here. All right. And, I have to be honest with you. I sat here like a slug, not doing it, but just do it. Look, you got 10 meters. That's delta Y. You got 80. And I said G is 10. So that's 100 times 80. The change in potential energy here, we'll just kind of keep it across, is 8,000 joules. If I did that right, I'm hoping I got the zeros I need. There's one there. There's one at there. There's one there, and there's one there. So it should be an 8 with 3 zeros. Let's see, this one, 80, 10, same thing, 8,000 joules here. So which one has the greater power? Well, it would be the one with the shorter time, right? So of these two right here, the greater power is in B. All right, keep moving. Now I got 64 times 10 times G is of roughly 10. So this is 640 joules and 8 seconds. Let's see. So I've got 8,000 divided by 8 seconds. I got 6,400 divided by 8 seconds. Uh, Obviously, B is bigger of the first three. That seems to be the biggest one. And now, of course, the last one, you got to look at the change in gravitational potential energy, because you got the 80 kilogram person, you've got 20 meters, twice as much, and you still have G is 10. So what is that? That's 200 times 800. That would be 16,000 joules for this one. But the time, although we doubled the energy, we more than tripled the time, didn't we? So this one, you look at it and you go, well, that was tempting, but I think the answer has to be B, because it has the best combination of the most energy change in the shortest time. D would have been a contender if it hadn't taken 25 seconds. So the 12 of you, the majority, but still, I guess, a little over half. Great job. I don't know if you had to pull out your calculator to do it, that's fine. But sometimes, particularly when you're checking problems, it is nice to be able to just do order of magnitude numbers in your head. To just did you plug the numbers correctly into your calculator? It's a good second skill to have in your tool bag of mathematical tricks. All right, I'm done with polls. Any questions on anything we've talked about today? All right, so I'm going to stop sharing this. I do want to make one point. There was a little bit of a discussion in both the reading and my pre-lecture video of potential energy diagrams. And I hope the chemists out there, or people who plan to take chemistry, appreciate how sometimes we model atomic bonding to make molecules as two objects connected by springs. Okay, and so there is a potential energy of a spring present, and the two objects just sit in the bottom of the parabola of the spring potential energy of one of the atoms in question. And I hope the chemist appreciated that discussion. How you cause two atoms in a molecule to break apart, what energy you have to put in, and it's a difficult subject to do a mathematical calculation on. But I hope you appreciated the kind of the fill in the details that might be related to your chemistry classes, if any of you plan to take them or are even majoring in chemistry. All right, time for me to do a problem. And so I'm going to shift over to today's worksheet, which, all right. Yeah, I trust. Connect your iPhone or computer. I must have hit the wrong button. So let's stop that sharing, and let's try again. Otherwise, I'm going to have to go someplace else. Oh, that's why I hit the wrong button. On me. Okay. On me. There we go. Now it's working. And it'll just take a second to do the screen mirroring trick. And put that away. Come on. And hopefully you see a problem in front of you. Anybody not seeing a problem? Not seeing the problem? And I've been done the initial drawing here. And let me clear that guy so it's out of my way. And all the little pop-ups that Apple thinks I need to see. Yeah, no, we don't want that. All right, get back to my screen here. And okay, so nobody's saying no, we're not seeing it. You've got two blocks, and you should recognize this problem because it was one of the problems we did when we did I think it was worksheet 9.2. Mass A, 5 kilograms, moving along the negative x-axis, approaching the origin. By the way, a number of people, as I was grading that, interpreted that sentence as moving to the left, okay? And it's just experience in reading problems. That problem's moving to the right. If it's on the negative x-axis, moving to the origin, it's moving right. And so that's why I drew that vector, which represents the velocity of 1 meter per second. And it was clearly, I went beyond just assuming you knew it. I put plus 1 meter per second just to try to avoid that confusion. Okay, it strikes block B with a 3 kilogram mass that's sitting right at the origin. Now, when we did this previously, it was an inelastic collision. In this case, the collision is elastic. The blocks conserve both energy and momentum during the collision. See how I'm not requiring you to have the definition of elastic memorized. I'll even tell you because I want to see you solve the problem. And so the question here, of course, is that's the before picture, right? Let me scroll down a little bit here and let's draw the after picture. We know everything before. We know the momentum of both particles before. We know the kinetic energy of both particles before the collision. But what about afterwards? And I'm not going to redraw the coordinate axis here that I've got, the number line, okay, because It is the x-axis, right? But now after, this is before. How about after? Well, I don't know what the heck is happening after. I got two unknowns, I think. Let's see. Here's a possibility. So they had this collision. Allison, it says you're submitting your worksheet right now. Shame on you. Shame, shame. Ned, I'm sorry, I'm just teasing. All right, so afterwards, though, we've got that there's A, and so that's the velocity of A final, and they've collided. And so if they're separating, maybe there's the velocity of B final, okay, because there's mass B. And I know neither of these two. I don't know that thing. I don't know that thing. In fact, I don't even know that that's the right picture. For all I know, A turned around and bounced back. I don't know that it didn't. Okay, so that's sort of the point. A could have been going that way. I just don't know until I start to do the problem. There's no way for me to know unless I can do the math in my head like Matt Damon did in Good Will Hunting. Okay, and I can't. I'm not that good. But, okay, so now this is the physics right here. This is what is expected in a physics solution. Okay, worksheets. I've drawn two pictures. And now what are the governing physics concepts? Well, the first one, let me scroll up a little bit to get myself some room. The first one is that the initial momentum, oh, come on, pen, don't fail on me. All right, sometimes if I just toggle back and forth, that does it. There it is. The initial momentum is equal to the final momentum. That's like writing F equals ma, right? Sum of the forces equal to mass times acceleration. That's your initial entry into the problem. You know that momentum is conserved. It says so right in the problem statement. Well, look at your picture. The initial momentum is mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial, but that's 0. It's at rest. And then you look at the other picture afterwards, and I'm just going to trust that things will work out. It's mass 1, velocity. Oh, I'm calling these 1. That should be an A, right? 1 is A. And so that now is a little sloppy because I didn't pay attention to what my labels were. So that's mass A, velocity of A initial. It's right there in my diagram. I don't know why I didn't catch it. This is mass A. Oh, come on, penmanship. I don't know if any of you know one of the physics majors, Sam Hickman. He's in my modern physics class. He writes on his iPad with the same app that I'm using, Notability. His penmanship is pristine. I am so jealous of his penmanship. It's awesome. Any event, velocity A final, that thing right there. But I don't know if it's to the right or the left. We'll see whether it comes out to be a positive, negative number when I'm done doing the problem. Plus mass B times velocity B final. B final. I don't know what that is either. I'm pretty sure it's to the right though. I've never seen a collision where this stationary object came back in the direction of the object that it hit. Okay, so the next step now is the numbers. This is 5 kilograms times 1 meter per second, which is 5 kilogram meter per second. And that's got to be equal to 5 kilograms times this thing right here. Now, for reasons that you'll see in a second, I'm going to call that unknown X and that unknown Y. You can write velocity A final, but the way I'm going to solve this in a second, it's convenient just to call that the unknown X. And the other one is 3 kilograms times the velocity of particle B. I'm going to call that Y, and that's a lousy looking Y. So there it is. That's my Y. Two unknowns is my point here. This is an algebra problem. I've got one equation written, but it's got two unknowns. To make it more algebra-like, I've called it X and Y. Okay, that's not a problem though, because I have another condition, don't I? I know that the kinetic energy initial must be equal to the kinetic energy final. That's the definition of an elastic collision. So that tells me that 1/2 the mass of A times the velocity of A initially squared plus 0, because the other mass, B, is at rest at the start, has to be equal to 1/2 the mass of A times the velocity of A final squared plus 1/2 the mass of particle B times, or block B times the velocity of B final squared. Okay, everybody see what I've done here? All right, now it's time to do a little bit of manipulation before I call on some resources to help me solve this. You know, the least information you have to type into a calculator, the greater probability you're going to get the problem right. So just taking a second to go, those 1/2s, they cancel. They just do, okay? And let's see, that leaves me with 5 kilograms times the initial velocity here, which was, I don't know why I'm putting a symbol right there. I know the number. It's 1 meter per second, and that's squared. So that is, let's see, a meter. Yeah, that's 5 joules, isn't it? Why am I writing the unit first? And my head's not working quite right. 5 joules is equal to, let's see, mass A, 5 kilograms times, again, this is going to be X, so it's X squared plus, let's see, 3 kilograms times what I've been calling Y, right? Y squared. All right, everybody got it? So what do I have here? I have an equation with 2 unknowns, and I have a separate equation with 2 unknowns. And so in 9th grade algebra, some of you probably much smarter, took algebra as an 8th grader even, because you were gifted and talented or whatever program you were in. You can solve those two. That's, I believe it. It's sometimes I get it wrong when I try to do it, but I can solve those 2 equations simultaneously and figure out what X and Y is. Any questions on it? The physics is done right now. Okay, everything I've shown so far is the physics. We draw diagrams that help us conceptualize the problem. We write fundamental concepts like momentum is conserved. So the initial momentum is equal to the final momentum. The initial kinetic energy is equal to the final kinetic energy. We recall what the definitions of momentum and kinetic energy are. We write out what that means for this particular problem, and we start hanging details on it, like 0 right there and 0 right there, because one of the objects is at rest. And then we put the numbers from the word problem into the basic physics equations in the 3rd step. And now we can outsource the work to the mathematics people. Okay, we're physicists. We like algebra. We enjoy it. It's fun. Sure it is. No, nobody likes it. Okay, here's a method to solve this problem. Okay, and I'm going to start, if I can get the share button back up, I'm going to start sharing my Google Chrome with you. And hopefully you're seeing a product called Wolfram Alpha. And it's the equalizer if you don't have the $200 or whatever the TI Inspire vintage calculator is, that will solve 2 equations, 2 unknowns. Some of the 84 series, 80 series calculators will do the same thing. If you don't own a calculator like that, you can go to Wolfram Alpha and you can hit algebra. Okay, and I want to solve a system of linear equations. Well, let's see if it works, because hopefully you noticed that one of my equations had X squareds and Y squareds in it. Let's see if this works though. I think it will. And you can see it shows you a sample problem. It shows you that there's your 2 equations. X plus Y is equal to 10, X minus Y is equal to 4. Solve it. Look what it does. It draws the 2 lines that represent those 2 curves and shows the intersection, and you're good to go. Let's try our 2 equations. And I'm going to drop the units because those gets handled separately, right? But we know that 5 is equal to 5 times X plus 3 times Y. Everybody okay with that? That's the momentum equation, right? I said 5 kilogram meters per second is equal to 5 kilograms times the final velocity of mass A, except I said X, but typed 5. See my point about the fewer keystrokes you type in, the more likelihood you're going to get the problem right. Luckily, I looked up and saw I typed in X plus 3 times Y. That's my first equation for momentum. There was a comma in there, and now I type in the second equation, okay, which was 5 joules this time, but still 5, I think. So 5 is equal to 5x squared. So 5 times x squared plus, and now the 3 kilogram mass, 3 kilograms times y squared. Anybody unfamiliar with that syntax of caret 2 to square something? Nobody's shouting out here. So I've got my two equations, and I'm going to tell Wolfram Alpha with this little equal sign, hey, go for it. Solve this for me. And I love the way this product presents the solution. See this straight line right here, okay? That is 5 is equal to 5x plus 3y. That's my conservation of momentum line. You may not have thought about it as I was typing in the other equation, but yeah, that's what the equation of a circle is. Hopefully at some point in your high school career, you realized x squared plus y squared is equal to a constant with coefficients is, well, maybe not a circle. It might actually be some ellipse right there because the coefficients in front of x squared and y squared are different. But you can see the intersection of the two, and those are the two solutions for these two simultaneous equations. That's neat, okay? And you can always just check. Wolfram Alpha is kind of neat. If I typed it in wrong, hopefully I would catch that one of my two equations is typed in wrong right there, okay? And then it shows me the solution. The x, which was the velocity of A after the collision, is 1/4 of a meter per second. The velocity of particle B, that's the 3 kilogram particle, it's moving at 5 force, 1¼ meters per second. Notice they're both positive. So my question about is A going to bounce back, or is it going to continue to go in its original direction, just slower, I guess? That's the answer. It was moving at 1 meter per second after it collides. Now it's only moving at 1/4 meter per second. B, which was initially at rest, is moving at 1¼ meters per second. The other solution is kind of interesting, isn't it? The other solution is the initial condition. That's what would happen if the two objects missed each other, right? A would continue to move at 1 meter per second. B would continue to be at rest. But the Wolfram Alpha solved the problem for you, didn't it? All right. Any questions on that? I'm going to stop sharing. I think Wolfram Alpha is a product that's out there that will do algebra for you. It will do calculus for you if you happen to be in a class where calculus is necessary. It will do some, you saw it did a nice graph for you. It will solve quadratic equations for you. It will do all those sorts of things that a very expensive calculator will do. And it's free, with one exception I'll warn you about. If you have a problem that is very time consuming for the system to work, if you're using the free version like I was right there, it is possible that a problem will take more than your allotted free share of the system's memory, okay, and computing power. And so they'll always help you with that. They'll sell you a subscription. Isn't life grand that way? But there's enough free here that for a 101 type course, or even most undergraduate courses, there's plenty of free capacity to do the math for you. All right, there are other products out there besides Wolfram Alpha. I just like Wolfram Alpha because if you've ever heard of a product called Mathematica, it was developed, it's a piece of software that you can buy, developed by the Wolfram company. It was very expensive, but it was very helpful to me as I was going through graduate school. Wolfram Alpha has a similar sort of flow to it. The syntax is similar, and of course it's free. All right, I want to move back to my worksheet here, and I'm going to just help you with the rest of the problems. No, not via cable. That's where I got in trouble before. Go back to the rest of the worksheet, and I want to just make sure that you have the ability to set the problems up, because that's often the questions I get on these things is, how do I start? And it's a legitimate question. Generally, and my answer often is with Newton's second law, with conservation of energy. But I want to make sure you see that on these two particular problems that you got to work over the weekend, because I'm a mean guy. All right. And oh, by the way, just to clear up what I was talking about, on my diagram now, I know what the answers are, right? This was 5/4 of a meter per second. That's what we just found. And this was 1/4 of a meter per second. Oh, pens, don't stop working on me. 1/4 meter per second. There you go. And this was not the answer. It kept moving in the original direction. All right, next problem here. And I think this is fairly straightforward with one exception. This problem requires you to do the initial vector step, okay? Because I ask you, what is the component of the force parallel to the ground, okay? And so you can see the force is this odd number, 122 newtons. I don't know why that, I stole this problem from somewhere, 122 newtons, and you have to get that component. And that's a problem from, I think, chapter 2, the first week of the class. And the question, I guess, is to get the x component of the force, which trig function do you multiply by? If this is a struggle for you, Wolfram Alpha will help you out. It will find components of a vector, but hopefully you know, do you multiply by sine of the angle given, or do you multiply by the cosine? Which is it? But that gives you the force. And then I think we said power was just equal to that force, the x component, times the velocity, right? And I think the velocity is given in the problem statement. So that's how this one, I hope, is a fairly straightforward problem. The only thing that you have to bring forward from earlier in the course is the ability to get this component right here, the force in the x direction, because that is the force which is parallel to the velocity, because the velocity is horizontal. We refer to this, by the way, as portaging. You have to portage that ability to get components from earlier in the semester into work and energy. That's an education person's term of art. All right, next problem, a little harder, I think. Okay, and in this case, we're looking at an elevator, right?
I have a question about the last
See
problem.
that again?
I have a question about the last problem. There are two
Okay, yeah.
different angles listed. Which one do you want us to use?
Hang on, let me see what that says. You said there's two angles given.
Yeah, it says 34 degrees in
Oh,
the
and then
problem and then
that's a
37 on the
typo.
diagram.
That's a typo. The answer is I would use the one that's in the word problem, because this is a typo. Thank you for pointing that out. Who are you? Who's speaking?
Emma.
Emma, you get an extra point for picking that out. You just caught a typo. So I'll give you an extra point on the worksheet. Let me write that down. Yeah, but if I ever do that, I will accept either angle. But I think my answer key is based on 34 degrees, because when I typed this right here, okay, that was the mistake. So my preference would be you use 34, but in a problem like that, if I make a mistake, I'll take either number, okay, either angle. And that's just clearly a typo. And the diagram was there to try to help, and by putting in a typo, I made it even harder, didn't I? All right, good question. Thank you, Emma. Appreciate it. Appreciate you pointing that out. All right, this one now. It's a work energy problem in power. Okay, so I guess the first question, you've got an elevator, you know its mass. It's being pulled up by the cable, which is being pulled by the motor. It starts from rest. It goes to a velocity of 4.2 meters per second, and that takes 7 meters of distance. So basically about 2 floors, I would think. Okay, and you want to know what's the work done by the elevator motor via the tension in that interval. Okay, and so let's see what equation, what concept helps us with that. Well, I think there's two things going on here, right? One is that the problem starts at rest and it goes to, what's this final speed, 4.2. I always look back now that Emma pointed that out. Did I get the speeds right in the two places I put the speeds? Yeah. So you have some initial kinetic energy, which is 0, and you have some final kinetic energy, which is 1/2 4.2 meters per second, and that's squared. Okay, and that's more. So you've got a change in kinetic energy here, don't you? Okay. I think the other thing you've got is you have a change in potential energy. So you can figure out what the change in kinetic energy is right there. Why? Because the initial Y position might be at 0 meters. That's a logical place to start. And then it goes upwards to, let's see, what does it go? 7 meters, right? So it goes up to 7 meters. And that was strange. That causes a change in kinetic energy, doesn't it? So you have to be able to calculate a change in its gravitational kinetic energy, okay? Because I'm sorry, I'm saying kinetic energy. Gravitational potential energy, it starts off at 0, And there is some final gravitational potential energy here, okay? And you have to calculate that. And I think we've said that the change in total energy, which in this case is because of the work being done, is equal to the change in kinetic energy plus the change in potential energy. So that must be the work done, right? And if you can figure out the time it takes to do that, okay, well, you can get power, right? Power is just equal to that work done over the time interval. Okay, and that's part B. I'm moving on to a hint on B here. Okay, average power supplied by the elevator motor over the interval. You got to figure out the time interval. Now, the problem is, anybody see a time interval? Yeah, me neither. Me neither. I didn't see a time interval. So I want to give you a little hint here on how to get that time interval. Let's see. What things do I know? I know the initial velocity. I know the final velocity. Let's see. Do I know the displacement? Yeah, 7 meters. So I think I know everything but the acceleration. Okay, know everything but that. So I can find the acceleration. And then once I've got the acceleration, I think I can figure out the time interval because the velocity final is equal to the initial velocity plus the acceleration, which I just found times the time interval, right? So the time interval would just be equal to the difference in velocities over the acceleration. All right, everybody good with that idea? And so now you have enough to figure out power. And then the last equation is, okay, once it gets up to its height, that it moves at a constant speed of 4.2 meters per second, how much power is being put into the elevator from its motor at that point. And of course, now you're just back to using power is equal to the force times the
Dr.
velocity.
Tukolsky,
Yep.
for the delta T equation, is that velocity final minus velocity
Yes.
final, or
Yeah, no, that
okay.
what should the second term be there?
velocity initial?
Yeah. And you know, it's actually I overstated. Who's that now?
Anna.
Anna, you get a point as well. Yeah, see what Anna's saying? That's initial. The bottom line is it's 0 anyway. So I was being a little careless with it, but yeah, absolutely, Anna, that's a 0, right? Yeah, so that allows you to figure out the time interval though, but thank you. It was not just bad penmanship there. I actually wrote F twice, so that's clearly wrong. All right, then the next part, once it's moving at a constant velocity, okay, you know what the force is, because if something is moving at a constant velocity, that force, that tension is exactly equal to the weight. So you're able to figure out that. If it's accelerating like it was initially, you can't say that the force is equal to the weight, but once it's moving at a constant velocity, you can. And so for part C, you can just find the force times the velocity to get the power, right? Now I've done about half the physics there. The remaining is plugging in the numbers with units and checking them. And you can use any product, any calculator you want to do it, right? I'm not sure if people have noticed the pattern here, because sometimes I'm asked about the 0 problem. I think I mentioned this, but if a problem is numbered in a worksheet with a 0, like this first one right here, I did that so that you know I did that one. You don't have to do that one. In this case, you have problems 1 and 2 to do over the weekend. And we've got now we're done. I managed to talk my way through the entire 50 minutes, but I've given you enough hints, hopefully, that you can finish up problems 1 and 2 and get the correct answer and hopefully follow the logic. I'd say number 2 is a fairly challenging problem. Okay, I've seen many students get it wrong over the years, and that's what it's multiple steps, and you have to think through each one. Problem 1, I think, is fairly straightforward. Any questions about anything? Thank you to Emma and Anna, who pointed out my mistakes here today. Unless there's any questions, I'll hang around for a little bit. I cannot come back at 10:30 today. I have some family issues to take care of, but we'll see you on Monday morning. Last chance for questions. Have a great weekend, and we'll see you on Monday. But I will.
Thank you. Have a good weekend.
I'm just going to stop the recording, but I'll stay here for any questions.